What is an insulator? What is a conductor? Why does it matter? Hi, I'm Jen Lucchese, Senior Vice President of Static Works.
And I'm Dave Long, Static Works founder and president. The terms insulator and conductor refer to the way a material behaves when electrically charged. Insulators resist the flow of electricity. In conductors, electricity flows freely.
In insulators, electrons are bound tightly to their atoms, restricting their movement. If an insulative material is electrically charged, its stationary particles block the flow of electricity, including static, so the charge stays in place on the surface of the material. That's why the rubbery insulative coating around electric wires prevents shocks. Plastics, PVC, glass, epoxy, nylon, and dry air are all excellent insulators. The soles of most shoes, often made of rubber, PVC, or leather, are also mildly to highly insulative. Conductors are the opposite of insulators. In conductors, loosely bound electrons move freely from molecule to molecule. If a conductive material becomes electrically charged, its moving particles allow the charge to flow or dissipate across the entire surface of the material. Water, carbon, salt, graphite, and metals like iron and copper are excellent conductors. The human body, consisting primarily of water and salt, is also conductive. Unlike insulators, conductors can be electrically grounded. In transporting electricity, conductive materials provide a pathway for currents to return to earth or ground.
Let's do a quick experiment to show you the difference between a conductor and an insulator. In my hand, I've got two discs. One is made of metal, one is made of plastic, and the handles are both plastic. In front of me, I have a static meter. What I'm going to do is I'm going to rub these two discs together. I'm going to measure them with the static meter. And as you can see, the needle moves all the way to the right when I put the plastic disc in front of the meter. That means there's a positive charge on here. When I put the metal disc in front of the meter, the needle goes all the way to the left. That means there's a negative charge on here. So by rubbing these discs together, I've generated a static charge on both of them, and the charge is opposite between the two different materials. Now what I'm going to do is I'm going to find out if I can discharge these discs. So I'm going to take the plastic disc, I'm going to touch it to this piece of ordinary LVT flooring, and as you can see, even though I've touched it to that surface, there's still a charge on it. Now I'm going to take the metal disc, I'm going to place it on the LVT flooring. There's still a charge on it. So we know that these two discs, metal and plastic, cannot be discharged when they touch this type of flooring. Now let's take what we call an ESD carpet. This is a carpet that has nylon, that has carbon fibers in it. Let's take the plastic disc, which still has a charge on it. Let's touch it to the ESD carpet. Charge didn't go anywhere. Let's try the metal disc. Charge is gone. Why did this discharge and not this? The reason this discharged is metal is a conductor. The carpet has conductive elements in it, and when they touch each other, they discharge. On the other hand, the plastic disc is an insulator, and regardless of what I touch it to, it's always going to have a charge because you can't ground an insulator.
Again, due to their high electrical resistance, insulative materials cannot be grounded. Most ordinary floors are insulators. When we walk, friction between our feet and the floor coverings generates static electricity. The static charge stays on the surface of our body and jumps or discharges to the first person or object we touch, a doorknob for instance, and we get zapped by a static shock. It takes 3,500 volts of static electricity for humans to feel a shock. A tiny charge as small as 25 volts can corrupt data, blow headsets, and damage or destroy sensitive electronic components. To prevent damage or disruption from static in a data center, FAA control tower, electronics manufacturing plant, or any other place where sensitive electronics are manufactured or handled, the floor must first transmit static charges safely to ground. The conductive properties in static control floors, like the ESD carpet we used in our experiment a few minutes ago, allow static charges to flow from the surface of the flooring material through the thickness to the conductive adhesive. The adhesive forms a conductive ground plane under the floor. Static flows across the adhesive ground plane to the conductive copper strips, placed along the perimeter of the room, and the copper strips carry the charge to the grounded electrical outlet.
But remember, electrical resistance is only one property of an effective static control floor. To prevent static charges from building as people walk, the floor must also have low charge generation.
To learn about charge generation and why inhibiting walking body voltage is crucial to preventing damage or destruction caused by static discharge, give us a call or visit our website.